I'm actually connecting from two devices, from iPad as well as from phone for some reason. So I don't know where I got disconnected.
No, I think I am saying that you are not disconnected, but Sitaram disconnected.
Okay. Okay, so I have written already the full expression of the Green's function that we obtain after substituting the uh, higher order correlation function f of omega. And now let's look at this expression. So this algebra was simple. I have basically just equated this Green's function to the form a divided by omega plus mu plus I eta plus b divided by omega plus u minus mu plus I eta. Because these two poles are there, I wanted to split the contribution, the coefficient of these two poles. So if I just equate it with this form and then find out a and b, and that's what you will get at the end. Okay. So now what does this equation of motion tells you? What are the two poles in this Green's function? So let me just write it here so that I can explain it to you again. So it means that if you are looking at the Green's function for the upspin particle, at that site, if there is a downspin particle as well, which is this part, then the pole of the Green's function is at omega is equal to u minus mu. Okay, except this imaginary part, which I'm writing. But if there is no downspin particle there, then the pole of the Green's function is simply at minus mu minus I eta. Okay, so there are two poles of this Green's function. If I forget about the imaginary part, the small negative imaginary part, you see that one pole is at minus mu on the real axis and another it has some u minus mu. So if you look at the imaginary part of this Green's function, it has one delta function at minus mu, another delta function at u minus mu. So there is a gap of the order of u. Okay. And as you can see, the u term appears in the pole only if there is a doubly occupied site in the system. It means if there is a downspin particle at that site, then the probability of having a upspin particle at some frequency omega has a pole u minus mu. But if there is no downspin particle at that site, then the probability of having an upspin particle with energy omega is has only a pole minus mu minus I eta. Okay, which is intuitively, I mean, this is what you expect intuitively. And it also gives you the correct single particle excitation gap, because in the single particle excitation gap, we know that we need a minimum energy of U to create any excitation in this system. U is a very high energy scale. And so as we were also doing in the similarity transformation, that we have some low energy states and then high energy states which are separated from it with an energy scale of U. And this is what we are getting here. And in the single particle density of states also, you will see that there is a delta function in the density of state at minus mu, then there is another delta function at u minus mu. So there is a gap in the spectrum of the order of u in the atomic limit, which tells you that you cannot have any single particle excitation by providing any infinitesimal small amount of energy close to the Fermi energy. So you have to provide at least an energy of the order of u. So this system is an insulator. Okay. And now similarly you can write down the expression for the Green's function for the downspin particle, and what you will get is that, okay, so this is what you will get for the downspin particle on the similar ground as we got this one for the upspin particle. So this is expression 6b. You should try to derive it just like I have derived 6a following the equation of motion method. Okay. Now I will try to come up with more simple Hamiltonians for which the equation of motion closes at least maybe at second order or at third order, so that you get some experience of dealing with the equation of motion method for the Green's function and also trying to identify its properties. And in the next class, I will try to tell you how to calculate the thermodynamic properties of a system using the Green's function. And I will also introduce what is known as the Dyson self-energy in general for any interacting system or a system where you have electrons as well as impurities. So any source of scattering can be captured with the definition of the self-energy. So these two things about the Green's function I will try to do in the next class. Okay. And when, hello.
Yes, sir.
So is this derivation clear for the equation Green's function for the atomic limit of the Hubbard model?
Yes, sir.
Okay. So whatever I have left, some steps in between, like the derivation of 6b, you should try to derive it on your own, both you as well as
Okay.
Sitaram. And only some things are left for the Green's function. That is the definition of the self energy and how does it appear in interacting or disordered systems, and then how to use the concept of Green's function to calculate certain thermodynamic properties of a system. That I will do in the next class. And after that, I will talk about the other linear responses like conductivity, susceptibility, etc. Okay. So Wednesday we won't have a class. I will. What is the date on Wednesday? Can you tell me? Today is 29th,
30th
28th.
March, maybe. 30.
30th March. Okay. So I won't be able to teach on Wednesday. Most probably I will take the class on Friday if it is okay with you. I will send you an email and a WhatsApp message ahead of time.
Okay.
Okay, at least one day before or several hours before, and then we fix for a time and do it. Okay.
Okay.
Okay, then I will close the meeting now and try to follow the notes. This Jamboard I can send you again. Try to follow the notes and also the book by Sondheimer and Donia. Okay.
Okay, and thank you.
Yeah. Bye.